All right, it's a great pleasure to welcome Daniel Tubenhauer, who is going to tell us about cells.
Yeah, thank you very much, Ben, and all the other organizers for the invitation. It's my last talk for this year, and it was a pretty crazy year, so I decided to keep it a little bit easy today. I hope you don't mind. Hope you won't. No one will be offended. I'm trying to tell you a little story about cells and why I like them, and what you can do with them. Sadly, I'm not going to talk about my first picture. This is a picture of cells in affine type G2, um, because kind of the flavor of my talk will be, I always stay in the finite types. And everything is kind of finite. So everything you will ever see is finite. And the categorification part of this talk is joint work with my usual crew. So Marco, Walter, Vanessa, and Joey. But the rest, like let's say 50 minutes of my talk, are pretty much well known, but apparently not as well known as it deserves to be. So I'm hoping to convince you that cells are pretty cool. And if that's the takeaway message for the end of this year, then I'm pretty much very happy. Okay, so let's get started. So don't worry, I only have a very few slides, so I will stay on those slides for quite a while. I want to start with a very classical story, which goes back to many people, but in the end, the main name to keep in mind is Green. In his work in the 50s or 60s of the last century on cells. And this is where all the notion related to cells, which you will see in my talk, originate really from. And I will spend quite a non-trivial amount of time just trying to explain this very classical setup. So what I want to fix is a monoid or a semigroup. I will click on this link here in a second. Here we go. So what is, just as a reminder, what is a semigroup or what is a monoid? Basically everything that is associative works, okay? So everything that is associative, that's a semigroup. I could formulate everything in terms of categories or group points if you want, but I will stay with a very easy setup of semigroups or actually monoids. So if you want to have an example of a monoid in mind, then the natural numbers. I like natural numbers. I don't like integers, if you want. And it turns out that there are quite a few of those semigroups. So you can just make a count and try to count the number of semigroups of order 8. And well, of course, every group is a semigroup, and there are 5 groups of order 8, so at least 5 semigroups of order 8. But actually, there are a lot of semigroups of order 8, something like 1.8 billion, according to Wikipedia. So this is quite a huge number. So everything you will ever see in your life is basically a semigroup. That's what I'm trying to say here. And everything I'm going to say applies to everything you will ever see in your life, in some sense. And you play around a little bit with those semigroups, and you realize, well, we all like and know the classical theory of group representations over the complex numbers, the classical one. And it's semi-simple. For semigroups, it's just not true. I mean, the easiest examples of semigroups will already be non-semi-simple. And even worse, if you try to classify indecomposables, that's pretty much hopeless. And that's what is called a wild representation type. And almost all semigroups are of wild representation type. So it looks like kind of studying representation theory of semigroups is pretty much hopeless. You have zillions of examples, right? Also potential counterexamples to any of your theorems. And everything is non-semi-simple from the beginning. Everything is just wild and complicated. And which I found very surprising is that Green actually tells us it's not hopeless. It's actually pretty nice. That's what I'm going to explain right now. So the examples you should keep in mind are like the natural numbers. Any group is a semigroup. Any multiplicative closed subset of matrices is a semigroup, right? So basically the notion of a semigroup is as weak as possible, such that you still have a satisfactory theory of matrix representations. The two examples will play a bigger role in my talk are Sn and Tn. I'm pretty sure all of you know Sn, that's a symmetric group in letters, and Tn is basically the same. You just instead of having automorphisms, so bijections, you just take any map, right? So any map from 1 to n to itself, that's an element of the so-called transformation semigroup Tn. Okay, so abundance of examples. Pick your favorite one. You can think of groups if you want. And then there comes this beautiful idea of green to force an order, a nice order on those semigroups. And he says the following, and all of them are the same. So let's just do the first one. The order on my semigroup, I pick two elements, x and y, in my semigroup, and I say that x is, let me get my own convention straight, x is left lower than y. Whenever I can find a z, here you go, such that you can factor y and you see x, and z appears on the left. So you can find an element, you multiply it from the left to x, and y appears. Then y is in some sense more complicated than x, so it's bigger and it's left bigger. He says it is left bigger. You can do, of course, the same for right and two-sided, just right from the right or from both sides, whatever. And this defines your pre-order on your semigroup, your elements. The semigroup. Whenever you have a pre-order, so this is the important part, the left-hand side. And whenever you have a pre-order, you can play always the same game as defining equivalence classes with respect to the pre-order. These are called the left, right, and two-sided cells. And this is just saying two elements are in the same equivalence class if if x is lower than y and y is lower than x. And well, the equivalence classes are usually called cells. These are left cells, right cells, or two-sided cells, depending on which kind of order you take. And in Green's notation, which I'm going to use in the talk, they're called L, R, and for some reasons I don't know, he calls the two-sided cells J cells. So L for left, R for right, and J for J, whatever. But I'm going to use those notions, and you will see very explicit examples in a second. The first one, which I would like to discuss in a bit more detail, is the example you see here, and I call it the group-like example. Right? So I want to tell you a huge theory which applies to everything you will ever see in your life, but it might be completely useless. Right? And here's an example when it is completely useless. If you think about those equivalence relations for a second, then certainly the unit in your potential semigroup, I'm kind of swapping between semigroups and monoids, doesn't make a big difference. Let me just stay with monoids. Then the unit in your monoid is always in the lowest cell. Why? Well, you can just choose z to be y in the upstairs equivalence, right? I could just let the z just to be y itself if x is 1. All right. But the same is true for invertible elements. So invertible elements always cluster in the lowest cell. In particular, if you have a group, then everything is just one cell. It's just one big cluster. And whatever I'm going to tell you will be pretty boring because I'm trying to use cells to have a reduction on a certain problem, which you will see in a second. And there is just no reduction for a group. Right? So a group just has one cell. There is no reduction. Theory applies, but theory is trivial. Okay. But for everything that is not group-like, actually the theory is usually pretty powerful. Okay, before I give you one explicit example and then several other explicit examples, let me tell you how I would like to think about cells. So those L cells are basically like left modules or left ideals, right? Whenever you multiply something from the left, you stay where you are. Those R cells are like the same from the right. Those J cells are really like bimodules. For the algebras, they will be bimodules. You will see it later. Or ideals, two-sided things. And there will be some funny guys, which I call H cells. They will show up in a second. And they're kind of, right. So when you have a left cell and the right cell, you can make it bigger by tensoring from the right side that you still have a left and a right action, you get a bimodule. Or you can make it smaller by tensoring from the wrong side, and you just get something that is multiplicative closed itself, that's the H cells, intersection of left and right cells, and they correspond to subalgebras. I want to think of them as being subalgebras. They are closed internally, but not externally. You have those 4 types of cells. And again, I'm using Green's notation. So he always calls this JR, L, JR, and H. Okay. Let me give you one super explicit example and then many more examples, which you probably will like because they kind of fit in the framework of this of the seminar series. So this is how I would like to draw cells. So this is the example of this transformation monoid that I just mentioned. So all maps from, in this case, the set 1 to 3 to itself, which I denote in one line notation. Okay, so this element here, 1, 2, 2, this just means 1 goes to 1, 2 goes to 2, 3 goes to 2. This is not an element in your symmetric group, of course, but it's a legal map. So it's an element in your transformation monoid in T3. And well, for now, you can just believe me, this is the back of an envelope calculation. You can do it yourself. You can check the slides on the website and try to do this calculation yourself, but this is how the cells look like. It's pretty easy calculation. In particular, notice the following. I will explain the notation in a second, but at the bottom, so the big rectangles, those are the two-sided cells. It's the biggest ones, they're the bimodules, they're really big. The columns, in my notation, I hope at least, are the left cells. The rows are the right cells, right? The left ideals and the right ideals together form a two-sided ideal. And those funny little boxes, these are the important players, these are the H cells, the intersections of left and right. So in my top, and they're ordered by the cell order. It's exactly the same order and gives you also an order on cells, not just on elements. And they're ordered like this. You have a lowest one, you have a middle one, you have the biggest one. And Green then probably has done several of those things. I had written down, it's pretty easy to write them down. And you will observe the following. So on top here, you see 3 H cells in one two-sided cell, and each H cell contains such a funny element, the 1, 1, 1 element, for example. And if you square 1, 1, 1, it's a map that sends everything to 1. If you do it again, it still sends everything to 1. So that's an idempotent. Similar for all the, this one, for example, 1, 2, 2 is an idempotent, 1, 3, 3 is an idempotent. Everything in the blue box is an idempotent. And you will see that in each blue box, there is precisely one idempotent. This is true in general. It's called idempotent separation. Green calls it idempotent separation. So each H cell contains either no idempotent, those are my white H cells, they don't contain any idempotents, or precisely one idempotent. And each idempotent, of course, appears in some H cell. And the next observation you would do, okay, this is a bit, let's do this one. Okay, if you just see it in the transformation monoid, then those two elements are not invertible, right? The symmetric group is at the bottom, as you can see. So this is your familiar symmetric group. And certainly those elements are not invertible. This element sends 2 to 2 and 3 to 2. But in a vacuum, just seeing as just these two elements in their multiplication, if I treat my idempotent as a unit instead of as an idempotent, then this is actually a group. And it's actually S2. Okay? So this is a unit in a group, and this is just a swap in the corresponding group. And Green says this is true in general. So whenever you see an idempotent in your H cell, you don't care about the white ones, okay? Forget them. They will be there, but you don't care. You only care about the blue ones, the one with idempotents. And this idempotent, it will be a unit in a maximal subgroup. Right? So here, of course, in the bottom, I just explained, in the bottom, you should always see the group, it's a maximal subgroup itself. And in each of the small boxes, if you consider them in a vacuum, they are also groups. And here another one. So S3, S2, S1 in this case. And Green says even more. I mean, you have idempotents. So idempotents are supposed to act as a 0 or 1 on simple modules. And Green says as soon as two idempotents land in the same two-sided cell, they either both act as 0 or they either both act as 1. And it's nicely compatible with the order. Meaning to each simple, you can associate a maximal of those cells, which doesn't annihilate it. Right? If you just check this idempotent annihilates my simple, then all other elements in this cell will annihilate the other simple module as well. Right? You only ever need to check one of those H cells, what it does, and then you are happy. And this is usually called the A packs. So it's kind of a numerical invariant you assign to your representation. Each representation survives up to a certain point, and everything above will act as 0. So you slice your classification problem of simples into those APCs. Okay.
So this is over any field?
Oh yeah, that's a good question. This works over any field. I don't care.
And just one more time, so J of E means what? J of E. Have as J of E.
Sorry. H of E means H contains an idempotent, and J of E means J contains an idempotent.
Sorry, J means what? What is J of E?
Sorry?
J of E is a cell, or sorry,
yes,
what?
J of E is a two-sided cell containing an idempotent.
So maximum with respect to some partial order that you consider
yes,
on.
Partial order is the same one from here.
It's a partial order on two cells, on two-sided cells.
I think I missed what you mean by killing it, because you compose and you'd still get.
It is 0 or 1. And if it acts as 0, I just say it kills it. So you would have, for example, simple modules on which this guy doesn't act as 0. It can't because it's a group. So no element here will act as 0 on a simple module. But it could be that this whole cell just acts as 0 on a simple module.
Okay, so when we're going to modules, you're adding some linearity, like you're allowing.
Yes, I'm considering representations over a field.
Okay.
So if you just have any idempotent and any simple module, its image is either the whole thing or 0, right? And
That's
you're looking only at idempotence in the semigroup, in this monoid, and somehow you're finding. So you single, I mean, so maybe can you just say a little bit more about this last statement on the page?
Okay.
I understand the part that you take an idempotent, apply to simple module, get either 0 or a whole thing.
That's right. And all idempotents within the same two-sided cell will spit out the same result, either 0 or 1. And everything above will kind of, as soon as you find something that acts as 0, everything above will act as 0 as well. Okay?
Yeah, the non-trivial statement is that it's this maximal is unique in this partial order.
That's right.
Yeah, thank you.
Okay. Okay, so let's stay on this slide for a little bit longer. So those cells kind of separate subgroups and idempotents for you. And what is the very surprising theorem by Green, which I call H reduction, is that's kind of enough. So again, I work over any field. I consider representations over any field, whatever you want. And the simples arrange themselves according to APCs, and the simples with a certain apex are one-to-one corresponding with the simples of the corresponding subgroup. Okay, let me get back to this picture. So you want to classify simple modules for T3. The only thing you need to do is you need to check your blue boxes. You take one blue box out of each bigger rectangle, and you classify the simples for those guys. And this gives you a classification of the simples for the whole beast. Right? You reduce it to just studying those funny blue boxes. Right? You reduce the whole problem to just studying those funny blue boxes. In my example here, for instance, it would be S3, S2, S1. So let's say I'm over the complex numbers, then I know that S3 has 3 associated simples. So the semigroup will have 3 associated simples, which are killed by everything above, but not by this cell. S2 has 2 associated simples, so there will be 2 additional ones, which are killed by the biggest one, but not by the rest. And there will be 1 associated simple module which survives the whole process, which is non-zero on the whole semigroup. And this is how it works. And I can always check this by just looking at my blue boxes. Right? So I have this huge picture. Semigroups tend to get huge, and I just look at my little blue boxes. And
so you're saying that classification of simple modules for semigroup algebras can be reduced to classification of simple modules for corresponding groups.
That's correct.
And can you reduce description of the quotient by the Jacobson radical for the semigroup algebra to the description of the Jacobson radicals for those group algebras?
Yes, that's also possible. I'm not going to talk about that, but Green also tells you how to do that. And he also tells you how to construct the simple modules by an induction process. So this is actually a pretty good statement.
Thank you.
Okay. I think you want more examples. So let me give you more examples. It's actually kind of fun. So maybe the transformation semigroup is a little bit okay. Yeah, you can study it, but I haven't seen it before, so who cares? But here comes an example you have seen before, and you can still apply H reduction. Okay. So I want to classify now for you the simple modules of the Temperley-Lieb algebra over any field. For any value of the circle which is not zero, you will see in a second why I don't want the circle value to be non-zero, so to be invertible. And I will do it basically in real time. A little bit cheating, of course, you have to trust my calculations, but this is really easy. You can do it yourself. So if you would write down the cells for the underlying monoid of the Temperley-Lieb algebra, so diagram times diagram is another diagram. This is how it looks like. In the bottom cell, you will see all group-like elements in the Temperley-Lieb algebra. In this case, it's just the identity. And in the next cell, you will see everything that has one pair of cups and caps, like this one. Here's another pair of cups and caps, and so on. And one step above, you will see everything that has two pairs of cups and caps, and so on. Right? So the cells are indexed by what I would call the through degree, so the number of strands that goes through. And it's pretty easy to see. As soon as you add cups to your diagrams, you can't get rid of them anymore. You just go up in the order. And well, you make this calculation and you realize, this is how it looks like. And so this guy itself is an idempotent if you ignore the fact that it spits out a scalar delta if you multiply it to itself. You could just, I haven't told you precisely how it works, but you can trust me in this case, you can just scale out delta from going from this pseudo idempotent, takes the eigenvalue, get rid of it, you get an idempotent. That's what I should put in the cell. But anyway, it doesn't really matter at this stage. It really doesn't matter. But this guy itself, if you just consider it in a vacuum, and let's say the circle, you get rid of this eigenvalue coming from the circle value, and this is actually, again, an element in a group, because it's kind of a unit of a trivial group, and similar for all the others. Right? If I ignore the fact that these are pseudo idempotents that I just rescale, then they are actually units in the group. Okay? So if you would like to apply H reduction, and you can, then the corollary of Green's theorem over any possible field, you can now, well, believe me that this picture here generalizes. In general, well, whenever I have whatever 500 strands, you just have cells ordered nicely linearly by through degree, and all H cells will look like this. They will contain those symmetric pictures, and they're all isomorphic to trivial groups. So Green's theorem then tells you that the simples of the Temperley-Lieb algebra are parametrized by possible through degrees, which is a pretty classical result, but it's just basically a corollary of this H reduction theorem of Green. Right? Let me make this. Let me repeat this. So you write down those pictures. This is easy. This is not hard. You look at the ones that contain idempotents. These are my blue boxes. This is also easy. And for each bigger rectangle, you choose one of your blue boxes. Okay. In this case, you're very lucky. All of them are isomorphic to the trivial group. So the classification of simple modules is just the classification of two-sided cells. And the two-sided cells are given by through degrees. So Green's theorem tells you are done. Okay. And he also tells you how to construct those simple modules. They will appear in what is called cell modules, whatever. Okay, so this is maybe an example you like a little bit more than the other one. So just classifying simple modules of Temperley-Lieb algebras within 5 minutes. The case delta not equal 0 is more tricky, but anyway, it works over any field. If you're still not convinced, let me give you another example that you might like. Kind of the same idea, but now I want to use the Brouwer algebra. So the Brouwer algebra is nothing else than the Temperley-Deep algebra, but now you allow not just crossing as matchings, but you can allow crossings as well. So you write down those pictures here. And you have the symmetric group part, and you have the relations of the symmetric group. So this is basically an algebra of tangles, if you would like to put crossings here. And you have the natural relations of tangles on this algebra.
Sorry, can I ask?
Absolutely.
So is it okay? So underlying the Temperley algebra is the semigroup of
diagrams.
Yep. So are you saying that the Temperley algebra is isomorphic to the algebra of the semigroup of diagrams after inverting delta? I guess I'm asking, what is the relationship between the Temperley algebra and just the sort of naive kind of semigroup algebra of diagrams? Are they isomorphic, or?
Strictly speaking, there is no relation. The point is that Green theorem still holds true for nice algebras like the Temperley-Deep algebra.
Okay.
But I'm getting there. At the moment, just accept the fact that this trick actually works. Okay.
No, I believe. Okay, good.
But also, I think if delta is 1, you do get a semi.
If delta is 1, then it's easy case. That's right.
That's right. Yeah.
I mean, this is the same example. If delta is 1, you get again the semigroup, but you can always rescale in this case. It's easy. Let me repeat for you. The Brouwer algebra is like the Temperley-Deep algebra. It's like tangles, but you ignore over or under crossings, and you have the natural tangle relations. In particular, you have kind of crossings, and if you do the calculation, then as promised by Green's theory, at the bottom you should see the maximal subgroup. The tangle algebra, ignoring over and under crossings, the maximal subgroup should be the symmetric group. And upstairs you see something that looks very much like the Temperley-Deep algebra. Again, everything is given by through degrees, and the J cells nicely arrange themselves according to through degrees. So we have, well, whatever, how many of them, always going down in steps of 2. Again, the same philosophy applies here. You see the symmetric group, it's your maximal subgroup, and in this case you see S1. Let me do a bigger example. So this is still the Brouwer algebra, now on 4 strands, and I just picked out one of the cells because otherwise I would have been unable to fit it on the slide. So this is the second cell, as you can see, through degrees 2, and you realize on the diagonals you have those funny pictures. But anyway, let's look at this one, the easiest one. So this guy is now on this little part here, acts as identity, as it should, as predicted by Green theorem. And then you have some crossing here. So this actually is isomorphic to S2. And that's kind of a thing you can observe in general. So if you do this Brouwer algebra case, that the H cells are always isomorphic to a certain symmetric group, and you just always go down. This is S3, S1. Okay. For a bigger example, you would have S5. You go down 2 because you do a cap pair, S3, S1, and so on. Okay. So you have this nice little arrangement of symmetric groups ordered by through degree, and you apply Green's theory of H reductions. And here I'm just doing it over C just to have the correspondence of the symmetric group to partitions, because then you get the classical result that the simples of the Brouwer algebra are indexed by partitions of n minus 2, n minus 4. Why? Well, because these are exactly your two-sided cells. You have the bottom one, you have one with 2 less, you have 2 less through strands, one with 4 less through strands, and so on. And for each one of them, the H cell is a symmetric group. So this is your classification. Again, basically without any kind of work, right? And the exercise I would like to tell you is that you should do the same for something that's called the partition algebra. That's a more fancy version of the Brouwer algebra. It works in the same way. The cells just get pretty huge. But anyway, so I think this is a pretty nice trick, right? So Temperley-Lieb algebra, you classify everything, you just write down cells. It's pretty trivial. All H cells are of size 1. You don't have to care for anything else. You don't care for the other elements. Those other elements are completely unimportant for the classification of simples. You just write down your H cells and you just count in this case. You do the same for other type of things like the Brouwer algebra. In this case, the counting gets a little bit more involved because you have symmetric groups. In particular, the result will depend on the field. But anyway, you don't care because a green theory works over any field anyway. Over C, you get this nice classification in terms of partitions of increasing, right? N, n minus 2, n minus 4. Let me do one more example and we can take a break. And then I'm going to algebras and then I'm going to categories. Okay. But before I'm going to algebras, I kind of want to cheat. I want to do another example for you. This is now really cheating. I will explain the algebras in a second. But let's say you want to classify simple modules of something like a Hacker algebra or just a group ring of the symmetric group. You could say, okay, you just explained that the group elements all cluster in one cell. So this is the best I can do. I just have to study it by hand. Or you can use the following trick, which I will justify after the break. You can actually choose a smart basis. Let's say you're very sophisticated and you would like to choose something like the Kazhdan-Lusztig basis. If you do the calculation for the Kazhdan-Lusztig basis, this is how it looks like for what is my type here, A3. Okay, so we have those. So this is not quite a back of an envelope calculation, but you could do S3. So this is how it looks like. You still have those funny two-sided cells. You have one of them for each partition of 4.
Daniel, is there a misprint at the top B? In the top B, is there a misprint in the top B for J4?
It'll be the longest element.
Is there a mistake in the
misprint?
That's just the longest element. So my notation here is this is a Kazhdan-Lusztig basis element for the element 1, 2, 3, 2, 1 with this Coxeter diagram, and this happens to be the longest element in this case. Okay, this is Kazhdan-Lusztig basis element for the simple reflection 1, simple reflection 2, simple reflection 3, simple reflection 1, 3, and so 1, 3, and so on. Okay. Anyway, if you do this calculation and you believe my calculation here, then you will see all those funny H cells, and actually all those funny H cells are up to scaling, and maybe up to scaling just again trivial. They're all of size 1, and to then get the well-known result that the simple modules of the Hacker algebra for type Sn, if you make all those cell calculations, are actually one-to-one correspondence with partitions of n, which is of course the result you all know because well, for the symmetric group, let's say. But it's still true for the Hacker algebra as long as you can rescale your elements appropriately. You don't see any zeros. So let's say generically. Okay. I'm going to discuss the case outside of type A in a second, or the algebra case. But just before the break, let me just repeat what we just learned. So you have the theory of cells. Here's a nice example. And as long as you have something like A times B is C, so you're really kind of staying in the case of a monoid, and you don't have any summands, which is basically still true here. And certainly is true for those diagram algebras. You can just completely naively apply green theory of cells, and you get a classification of simple modules basically for free by looking at like Michael said, as those maximal subgroups, and you've reduced everything to the study of groups. You have reduced the study of semigroups to the study of groups, and not just to the study of groups, but also to much smaller groups, right? So the Brouwer algebra, for instance, here is of dimension 105. So it has 105 elements. It's of dimension 105. and you only need to consider S4, S2, and S1, S0 in this case. So it's pretty much a huge reduction of the whole process. That's why it's called Green's theory of the age reduction. Okay, I think it's a good time for a break.
All right, let's take a 5-minute break. Reconvene at 1:42.
Daniel,
Yes,
even though this is a break, I assume I can still maybe ask a question.
of course.
So you might have answered this already, but I just was curious. So this Green's theorem, which by the way is anyway probably one of many Green's theorems.
Yeah,
We're not the Green's theorem that I teach my calc students. Anyway, so is there a construction from like, so so first off, are you saying that every J cell is semi-simple? That's a result of this. So if you take
over the complex numbers, no, any H cell over the complex numbers, yes, because it's
H cell. Okay, so if your H cell is some group, some finite group or whatever G, is there a construction that, given a central idempotent in the group algebra, kind of lifts it to, what do I want to say? I guess I can also think of the J cell as being a monoid, right? Is there a construction that lifts an idempotent in an H cell to an idempotent in the J cell?
An idempotent in the H cell to an idempotent in the J cell.
Yeah, I guess I just mean.
I'm not sure what you mean. I mean, in a group, you don't have any interesting idempotents, right?
I mean, but you have idempotents in the group algebra, I guess.
Oh, yes, I think that isn't so easy. So at the moment, I'm really relying on the fact that A times B is C on the nose and not just a linear combination.
Okay. So if I wanted to, right. So the simples, I also think of them as parameterizing central idempotents.
Yes.
And you're telling me it's not so easy to pass from central idempotents in the H cell to central idempotents in the J cell.
That's right. You will see actually a counterexample, I think, to what you have in mind.
Okay, thanks.
Right. So in all games I just played, it was extremely crucial that diagram times diagram is diagram. Whether there is a scalar or not doesn't matter, but diagram times diagram or element times element is element.
Mm-hmm.
So no linear combination.
Mm-hmm.
There you go.
Sorry, I just want to ask one more thing. So this statement about Heck algebras, this is over any field? Again, just like everything else?
Not quite. So what I always want here, for example, is that I can rescale, right? So for my example here, I really want to rescale all the numbers you see if you square those Kazhdan-Lusztig basis elements. Like if you square this one, there's a 3 factorial, and you need to be able to divide by 3 factorial.
Okay. So is this the same field over which the Heck algebra is semi-simple?
In this example, probably yes.
Okay. Thanks.
But actually, in the end, I don't need it. I just needed to make it fit to Green's theorem on the nose. So in all of these examples, you can make it work if those parameters vanish. You just don't get any idempotents. You would need to ignore those cells.
Are there lots of two-sided cells that have no idempotent H cells?
Yeah. In general, there could be lots of two-sided cells which don't have any idempotence at all. For cellular algebra, for example, that would be the difference between if it's quasi-hereditary or not.
Are there ones that have idempotence but have like a white box that have an entire row and column of white boxes?
Ones that have idempotence, an entire row. Probably yes. There are so many semigroups. I don't know an example right now.
Okay.
So basically anything can happen. There are so many semigroups.
Wait, so Ben, your question was, is there a two-sided cell and a pair of H cells within that, one of which has an idempotent and the other doesn't?
No. My question was whether there's a whole column and a whole row that don't have any idempotence, and yet other ones do.
So like in this example, would it be possible to have a whole white row, for instance? That's what he's asking.
Well,
as I said, I'm not sure. I think it's not possible, but I'm not 100% sure.
Okay.
I have another kind of question. Is there? Oh, sorry. Somebody else is trying to ask.
I was just going to say let's start again because.
Oh yeah.
The questions for the end.
Okay.
Okay. So should I just start again?
Yes, please.
Okay. So as a reminder, we just discussed semigroups, and now I want to throw in some algebra. So I want to have some sums. And I think in this case, it really goes back to Kazhdan-Lusztig, so the first idea. It's kind of a reformulation of green theory, but in linear. And what they do is the following, basically. So for an algebra, like there are two problems, which you will see in a second. So first of all, I want to fix a basis. For semigroup, there wasn't really a choice of a basis. It would just take the group algebra and choose the obvious, or the semigroup algebra and choose the obvious basis. But in general, for my finite dimensional algebra S, I want to fix a basis. And if you would compare this slide to this slide, you will see it's actually exactly the same, except that I have now this funny symbol here instead of equality. So I'm saying X is left lower than Y if I can find Z such that Y appears with a non-trivial coefficient if I express Z times X in terms of my chosen basis, right? Here's my choice, my chosen basis with a non-trivial coefficient. And the rest is just really the same. It just define left cells, left orders, right orders, two-sided orders, whatever. You have left, right, and J cells. And now left cells are really like left modules, and right cells are really like right modules. And J cells are really like bimodules and so on. And the same idea is still, the same idea of groups versus semigroups is still true. So if I would take, of course, just S to be the group ring of my group algebra, and I would choose the basis of group elements, then I get trivial cells. But the Hacker algebra example I did 5 minutes ago already says that there is some strange choice of basis involved. And what I would need to do here is the right notion of an H cell is now, I take all elements in my cell, in my H cell. I'll give you an example in a second. And they will still form a subalgebra, but only a subalgebra up to lower guys. Okay? And you just need to kill those lower guys, and you have a sub-quotient algebra, whatever you want to call it. Okay, so before I don't have that. All H cells were groups on the nose. I had no need to quotient out anything. Here I don't get quite subalgebras. I get subalgebras up to bigger elements, and I need to get rid of those bigger elements. So here's an example. Same notation as before, but now I'm doing Kazhdan-Lusztig theory in type B2. So B2, my elements are named 1, 2, and they have a 4-term rate relation between them. So this one is, for instance, the longest element. And this is how the cells will look like. It's kind of the same story up to a slight glitch, okay? So you have some nice cell order. You have two-sided cells, you have left cells, you have right cells, you have J cells, you have H cells. And all H cells are formed like some nice subalgebras. Okay, this is just has one element, this is trivial, this is just one element, this is trivial. It's kind of a trivial subalgebra like a trivial group. Again, up to the fact that this actually is a pseudo-idempotent, so you need to divide by its eigenvalue, but that really doesn't matter. The point will be the middle cell. In the middle cell, you actually, after rescaling, see Z mod 2 turning up. Okay, so B1, if you just consider this blue box here, B1 is actually a unit in the cell up to an eigenvalue that you don't care. And B121 times itself will be B1 up to some things you don't care, you already killed. So this is basically Z mod 2Z. And then you would do another count, right? You would just try to apply Green's H cell reduction. You would count, well, trivial group probably has one simple, trivial group probably has one simple. Z mod 2 looks like it wants to have two simples. So you would count 1 plus 2 plus 1. You get 4. Actually, you want 5 simples. Shit, Green's theory doesn't work anymore. This is a kind of a little of a shock, right? You do this whole theory for semigroups, it works for semigroups. As soon as you throw in sums, it doesn't quite work. Just to tell you the general story, you will see an example in a second. You could hit the right number. If you're lucky, you could hit the right number here. If you're unlucky, you don't, but you never overcount, you only undercount. So Green's theory will still produce some simples for you. It might be that you don't get all. Okay, so here's an example. For the experts, the Kazhdan-Lusztig basis is not cellular in outside of type A. This is what's going wrong here. I will come back to this in a second. Just keep it in mind. Keep in mind that now everything depends on my choice of a basis. To make it completely explicit, I ran through the calculation for the same example, but I decided to renormalize my basis elements, those two, right? So my B prime 121 is just this element, and my B prime 212 is just this element, and now you get completely different cells. And you get the funny, the following funny thing. Now all H cells are just K up to rescaling, and you then just count 1, 1, 1, 1, 1, and you hit 5. So you actually hit the right number. Very, very, very strange. Good. So 2 examples, 2 different bases. One doesn't quite work, and the other one works. Well, let's try the next case. So this is what is called, well, here's the Coxeter diagram. This is what is called type H2. And I'm just sloppy. I just choose the basis I like, the Kazhdan-Lusztig basis, and do the same calculation. Basically the same pattern. So K, Z mod 2, and K. And now you count 4 again, and this is the right number. Also, this basis is not cellular. Let me just say this again. You still count the right number. And this is kind of a whole. So let me just summarize what we have just seen. If you really want to do the reduction in linear, you run into 2 problems. The first problem is everything depends on the choice of the basis, right? Choosing 2 different bases might end in, and they're not horribly different. I just kind of adjust 2 basis elements, but you might end in 2 completely different cells, right? Cell structures. It can get actually as bad as you want. So this could be super complicated, and this could be super nice. Everything basically is possible. And if actually the formal statement is the following, and you can prove that. So if you have a situation like this, and you have H cells of varying sizes, like 2, 1, 1, 2, like this one, then you will undercount. Okay. If you have H cells which are all of the same size within one, I'm just talking within one J cell. I might be a little bit quick right now, so stop me. Within one J cell, you have H cells which are all of the same size. Like, well, for those it's always trivial, of course. But for the middle one here, for example, then you're fine. Then H reduction applies even in the linear setup. Same here. This is a kind of funny example. So here, the bottom and top one are boring, but the middle one, it still works out. because all H cells are of the same size. They're kind of inflated by a group. You've seen this example in this Bauer algebra, where H cells got pretty big, but it was basically just the trivial group inflated by a symmetric group. And the same is true in this linear setup. So green theory in linear, which I don't want to formulate a theorem because it's written nowhere, but green theory in linear basically is, okay, if you choose your basis in a good way, such that all H cells are of the same size within one J cell, then you can apply H reduction. Otherwise, you will undercount the number of symbols. And there's one case before I go to the last 5 minutes to the categorification. There's one case, this one for instance, where all H cells are of size 1. This is usually what you find in the literature under the notion of cellular algebras. So this whole theory of cellular algebras was developed in the 90s by Graham and Lehrer to kind of have a green theory in linear, and they did calculations like this, and you find it doesn't quite work. But there's one case where it really works very nice, namely when all H cells are of size 1. Right? When all H cells are of size 1, then first of all, Green's H reduction still applies, although you're over an arbitrary field, over an arbitrary finite dimensional algebra, it still applies. And even better, because all H cells are of size 1, the classification problem is trivial. You always see the ground field, right? So you just count the number of relevant J cells, right? You just count the number of relevant two-sided cells, which have such an H cell, which have such a blue H cell, and you're done. And that's the whole point about those cellular algebras. But it holds more general. So whenever you have J cells of the same size, you're still happy. And the main question is how to find a good basis such that, right? So the whole point about all this nonsense about cellular quasi-hereditary algebras is not that an algebra is cellular or an algebra is quasi-hereditary, but rather that you can write down the cells and the cell structures explicitly. Without writing down the cells and the cell structures explicitly, an H reduction is completely useless, of course. Okay. Okay. Before I go to the categorified picture, I hope you will forgive me that in the last 5 minutes I need to be a little bit sketchy, of course. But let me just repeat what we have seen. Okay, so we started with Green's amazing theory of cells in semigroups. Semigroup is the case element times element is element, no linearity. It works over any field. You reduce the whole classification problem to the study of those funny H cells, which turn out to be maximal subgroups. So we reduce the whole study of studying monoid representations to the case of studying group representations. That might also be the reason why we've never seen any good literature on monoid representations, because, well, it is basically the representations of groups. And this applies in quite some generality. Just an example, something like a month ago, I was looking for literature on representations of groupoids, and you don't find anything. Why? Well, a groupoid is just a fancy version of a semigroup, and you, of course, can reduce it to the studying of groups. Just as another example. Anyway, so H reduction, reduce it to those H cells. Works amazingly well. In all examples where A times V is C, up to a scalar. You don't care for the scalar. You try to do the same in linear, like following Kazhdan-Lusztig, and it almost works. You run into some trouble, like, I have to choose a basis, and I might undercount if I choose the wrong basis. But if you choose a correct basis, it still works. Right? So the real problem here is kind of the choice of basis. And yes, just to answer your question, for any finite dimensional algebra, you can find a basis such that it works. Okay. The real question is how to find the basis. Okay. This makes you a little bit, well, I don't know. I'm really a big fan of Green's original theory, and in linear, it's just a little bit nasty. It's not that bad, but it's a bit nasty, right? You have to choose some stupid basis and whatever. So you might wonder about the categorification. And the really surprising fact is, on the categorical level, you will see it in a second, it looks exactly like the linear level. but on the categorical level, you recover the original H reduction without any problems, which is an extremely surprising result, in my opinion. If you have done all those funny calculations in those algebras, it just doesn't really want to work. In some sense, it works, but not really. It's a bit nasty. Okay, so I have 4 minutes left. Let me just run you through it. And I've written down all necessary details on the slides. If you really want to see it, then please read the slides. I don't have in 4 minutes. I just don't have the time to explain anything in details. Just the main message. Just try to get the main message. And the main message is as follows. So what is green theory in categories? That's what I want to do, green theory in categories. And it's the following notion. So we have a reasonably nice monoidal category. Let's say monoidal category is the categorification of an algebra, of course. And I don't have to pick a basis anymore. I have a God-given basis on the Grothendieck ring, the basis of indecomposables. So what I do is I just replace the symbol from before, this symbol. I just replace it with an even fancier symbol, which means basically exactly the same. So I say X is left lower than Y, and now X and Y are indecomposable objects in my additive, whatever reasonable monoidal category. And I say that X lower than Y if you can find Z such that if you take the direct sum decomposition, you will find Y. That's exactly what the symbol means. Okay? The rest is exactly the same. You can define H, two-sided left cells, right cells, two-sided cells, H cells. You can define the associated categories by just mimicking what you've seen on the algebras, by killing bigger friends. There will be subcategories, sub-quotient categories, whatever you want, in the reasonable sense. Everything that looks group-like will have a trivial cell theory, like semi-simple categories with an involution. So what people call fusion categories. Like vector spaces will have a very boring cell theory, or braided vector spaces, more two vector spaces, if you like super things. All of this will have a boring cell. But there are still those semi-group-like objects out there. They have interesting sub-theory. You can apply it. It's the same notion, right? I just replaced the sum by a direct sum. That's basically what I did. Okay, just to give you some examples, and then I will state the main theorem. Getting some kind of vacuum, and you need to believe me that I've done my homework and I've defined a reasonable categorification of a finite dimensional algebra, not just a random one. But basically, if you like, come back to my first picture, cells, if you like to think about something like tilting modules, cells are actually tensor ideals. For Zergel bimodules, cells will be the usual Kazhdan-Lusztig cells, basically because you define it on the indecomposable objects, and you need something like, of course, the categorification theorem that the indecomposable objects will categorify the Kazhdan-Lusztig basis. But you should ask Ben for some details about such a theorem.
Daniel, can I ask a question?
Absolutely.
So I think so. You're categorifying not just a finite monoid, but I think you're categorifying a finite dimensional finite rank algebra with a positive basis and a symmetric form, and then the dual object corresponds to the bijoint functor. I think it looks to me like you're categorifying
That's
not
basically
just a monoid, but this kind of finite dimensional algebra with a positive basis.
I'm basically categorifying a finite dimensional algebra with an involution. That's right. Okay. There's a nice calculation you can try to do. It's not so hard. If you wonder what the cells for Tucaccimuti categories are, so those categorified quantum groups, you will find that you can kind of push everything to some kind of cyclotomic Taylor algebra, and you will find that all H cells are actually of size 1. This is, of course, hopefully completely wrong for something like Zergel bimodules. Anyway, I'm out of time, so let me just run you through the last example. This is, of course, not a self-contained example. Well, maybe not, of course, but if you know Zergel bimodules, this is an easy example for you. If you don't know Zergel bimodules or never done the calculation for Kazhdan-Lusztig based elements, this is just the same as for type B2. It's really the same picture, right? Instead of writing K, I write now vect, which is the categorification of K, instead of Z mod 2, I write vect Z mod 2, so Z mod 2 graded vector spaces. Really the naive categorification of Z mod 2. And I haven't told you what simple modules are, but there's a reasonable notion of simple modules in this categorical setup. You would do the count again. It's 1 plus 2 plus 1, you get 4, and that's exactly the number you expect. In contrast to the decategorified picture, where I wanted to have 5, right? So here my same picture, decategorified, counting is wrong, picture categorified, counting works out. Okay. And the surprising theorem is then exactly what you expect. The H reduction just holds on the nose without any catches on the categorical level. So you have again a notion of an apex of a simple. It's exactly the same statement. Just put some categorical nonsense everywhere. So simples of your big category are indexed by simples of those small h things. Yeah. And I think I'm already over time, so let me just give you two applications of the theory. One is a pretty direct application, the other one is trickier, but it actually also works. And then I'm done. So if you want to, let's say you want to classify two simple modules of something like Kazhdan-Lusztig 2 categories, you know some simple modules, as well as the classical categorifications of Tubenhauer and Schwann-Wauquiez. And actually the H reduction will imply that there are no other two simples. Okay? So the classical categorification of the simple representations downstairs are also the simple representations upstairs. And you can play a similar game for circle bimodals. It just gets much more trickier because circle bimodals are pretty hard actually. Anyway, but we can do that. Okay. So thank you very much.
All right, let's thank Daniel. Great. Are there, that's wonderful. Are there any questions?
Yes. So I was just curious. So what does this say? Okay, so I'm curious about this kind of fifth representation in type B2.
Oh yes, let's go back to type B2. I like type B2. Yes.
Yeah. So I guess, do you have an analog of these B primes in the categorical in circle bimodules, or?
No, the point is you don't need them. So the trick which I used here is, okay, the Kazhdan-Lusztig basis doesn't work for green theory outside of type A. But if you, in type B, if you do the multi-parameter version, and you take the multi-parameter Kazhdan-Lusztig basis, this is exactly my prime basis here, that actually works. But I can't categorify the multi-parameter algebra. But you don't need to. The point is this counterexample vanishes in some sense on the categorical level.
Daniel, I remember there being some paper with you and Marco Mackay on like exactly this particular cell module. What happened in that paper?
Yes, so the point is what you really want to classify downstairs are not simple modules, but integral indecomposable modules. And if you really care about integral indecomposable modules, then you have an H reduction. Okay. If you care about simple modules, then this two-sided cell has two cell modules. Let's say the two columns, and each one of them contributes one simple, which is supported on the diagonal, and an additional one which is supported on the off diagonal. And you can't see this off diagonal element if you just concentrate on the diagonal. But if you don't allow simples, but you don't allow to invert your scalars, you want to have something integral, then you can't split it off, and you get the same, you get the right number. You don't get an additional one. So the problem here is that this H cell here only sees this cell module, but there's another additional simple missing in the other cell module.
Wait, so when you categorize the thing, so are you saying the combination of these two is what you see at the categorified level? So
what I'm saying at the categorified level is the two I would count here are just the two corresponding cell modules. They don't break any further because
What
what was the decategorification of an equivalence upstairs? It's an integral equivalence downstairs, something over the natural numbers. And you just can't make those any finer anymore. And then you count the right number.
So are you saying 5 is the wrong number, I guess? Or are you saying
5 is the right number of simples, but it's the wrong number from the viewpoint of categorification. 4 is the correct number from the viewpoint.
So maybe another question that I'm trying to ask is, do the two simples categorify simples, or do they decompose further at the decategorify
Here's
level?
an example where the answer to your question is no. Two simples don't categorify simples. In this case, the two simples are the categorification of the cell modules. You have two of them. Here's one, and here's one. But both of them decompose into two simples again.
Mm-hmm. So you, okay.
Okay, here's a good way to remember it. You just can't, or at least I don't know a good way to categorify simple modules as simple modules, as long as they are not integral, right? Over the complex numbers, you can just divide by something and you can make things much smaller. Categorically, you can't do that. So things cluster together into what is called an indecomposable over the integers.
Right.
It's just a huge coincidence that for two Kazhdan-Lusztig categories, you actually categorify the simple modules.
Mm.
So then one thing I'm confused about is in.
Yes.
Oh. Never mind. I was if you're working over Z, say, or
Okay.
characteristic 2 or something, and then you can categorify B1 to 1 prime.
Here.
As with a complex.
Yes, absolutely. I mean, I have a really naive setup in categorification. I just additive, no complexes, very naive. Right. I'm not saying they are uncategorifiable. I'm just saying my additive version can't categorify them.
What's the difference between H reduction and strong H reduction?
Very nice. A very good point. So whenever you read those things, I always had this extra. So actually, it's a bit stronger. It's not just a one-to-one correspondence on simple objects. It's an equivalence of categories for the simple modules. This is just a pretty stupid statement decategorified if you have something like Schur's lemma, because I mean the categories of simple modules downstairs are not very interesting if you have Schur's lemma. Right? So the objects here are just direct sums of simple modules by Schur's lemma. Home spaces are trivial. You already know a one-to-one correspondence of the simple objects. So this is basically the same statement. Okay. The point is the same is true categorically. You have a one-to-one correspondence on simple objects and you have an equivalence of categories. But now the equivalence of categories is not trivial. Simple modules upstairs do not satisfy Schur's lemma. So the strong H reduction is just saying it's actually stronger than just a bijection. It's really an equivalence of categories, not just matching simple objects.
Thank you.
Yeah.
I had a quick question from before, Daniel. In the original semigroup setting of green, do all the H cells inside a J cell have the same size?
No, in general not. They're just Morita equivalent. They don't need to be isomorphic.
Okay. So this is sort of, okay, never mind.
I just happen to pick examples where they're all of the same size.
But... and so for Heck algebras, you made a comment for every finite dimensional algebra, has a basis,
Yes.
which is cellular, or with respect to which all the H cells have the same size within a JSON?
With respect to, okay, so you can always find a basis such that all H cells are of size 1.
Okay. And does this mean literally, so you said that this means literally that the basis is cellular in the sense of Graham-Lehrer?
Not quite. So they have an extra assumption on having an involution, which forces your cells to be squares. I'm just saying all H cells are of size 1. You could end up like
okay.
this one, like where you have a rectangular two-sided cell and not a square two-sided cell.
I see.
The real difference between cellular algebras and all algebras is that cellular algebras have an involution which behaves nicely with respect to the cells.
Mm-hmm. So is it fair to say that we can only sort of categorify cellular algebras? Or, I mean, I guess maybe.
I guess invalidation corresponds to bijointness, right? In the
That's right.
logic,
So having a nice
invalidation corresponds to passing to the bijoint functor.
Yes. Right. So I mean, is it fair to say? Probably it's not fair to say, but at least in my setup, you always end up with something having an involution.
But so when you talked about monoids, you just assume involution is identity.
Okay, there's a slight difference between semigroup and monoids, and there's a general philosophy. Whenever you don't have an identity in your semigroup, you can always adjoin a formal unit and make it into a monoid. So the statements are the same for semigroups.
No. My question is different. I'm asking, so you just have a monoid, so you assume that the involution is identity, because everything is based on having involution. But you didn't talk about it at the beginning, so I assume that on the monoids, involution is the identity.
Yeah, no. You need to have an anti-involution. The anti-involution should swap left and right cells, such that you get square-like two-sided cells. An involution is not okay, an anti-involution.
So somewhere in the story, you introduce involution on a monoid. Somewhere you introduce the involution.
No, for monoids, you don't need it. For algebras, you need an involution. For monoids, you're happy. Monoids are too simple.
So wait, algebra is a finite rank algebra over Z with a distinguished basis, and involution on the basis of multiplication has non-negative integer coefficients in that basis.
Yes.
And then you can do theory of cells.
That's right.
Did you say that any algebra has a basis for which all the H cells have size 1?
That's right.
Okay. So every algebra has a basis. The H cells have size 1. The special thing about cellular algebras is that they're squares.
And that H cells have size 1, that's over the complex numbers or over any field?
I think you need to work over an algebraically closed field, but then you're happy.
But you don't need to restrict on what your denominators look like. You can do it.
Cool. I say we thank Daniel again and stop the recording. I don't have the candle after this time.